Hello and welcome to our fifth Barn of Tomorrow session. Thank you for joining us again this week. Brett Ramirez is going to be here to finish off our presentations on preparing for winter and minimum ventilation. Brett's kicked the series off with a great presentation on what we might be moving for to technology, and super excited to have him talk about something that gets brought up again every year. What can we do to make our winter and minimum ventilation situations work better in Iowa? So definitely an important and timely topic. While it's pushing 85 today, I'm sure chillier days aren't that far in the future. So with that, thanks for joining us, Brett, and the floor is all yours.
Thanks, Dan. And kind of just segueing off that, why it doesn't seem like it's going to be winter time anytime soon, but it'll be upon us before we know it. So, again, I thank you all for tuning in today. And while much of this is the same every year for everybody, it is important to understand why it's important to prep for winter ventilation. And when we get into those lower ventilation rates, because it's going to have an impact on mainly our heating fuel usage and the environment inside our barns. So, really, with this is to kind of go over some of the things you probably all have heard before, but just to reiterate them and really demonstrate the importance of those so we have a good environment and we optimize how much energy we're using to keep that environment good. So I'm going to go through a bunch of different things. I will preface this is all swine focused because if you know me, that's what I do most of the time. So um, I think a lot of the concepts are easily translatable to other species. There might be some nuances with how different barns operate, but for the most part, the concepts are similar, just they might be applied a little bit differently. So I'm going to start off with sharing access to a checklist. This is again mainly for a wean to finish, grow finish, nursery style barn. Um, but really the goal here, and this is why I like checklists, it has not only does it help guide one through all the different components of the ventilation system and what needs to happen as we go from summer to winter, and then vice versa. We have another checklist for our winter to summer, but also has some accountability and really make sure that everything is going to get done right, and that puts us for the best chance of success during winter ventilation. So you can go ahead and scan that QR code, or I have the search terms that you can use in the Iowa State Extension store on the web. Right. So getting ready for winter can be easy, right? There's a lot of things that we know get neglected, things to fix, things to repair, things that we know we shouldn't do, but all those things eventually have to get done at the end of the day, right? First step, troubleshooting. We have to recognize when we know something isn't right, right? Just being able to develop that intuition on, this doesn't look like I feel a draft here. It's really wet and muddy in this spot. I see gaps here. I notice my cones aren't there. I notice the belt's loose. I notice that fan's doing something, right? Just having that intuition that when you're walking a barn doing those thousand other things, just try to be able to recognize when it's not right and then let somebody know um, that it's not right so it can get fixed, right? That's why start early and then have the right tools. It might take having some additional sensors or whatnot, but we got to have tools to be able to measure because if you don't measure, you don't know. Maintenance, a lot of problems could be avoided with routine maintenance. Don't wait until it hits you. Um, Again, use that checklist because that's going to help drive that maintenance process forward because as you check those off, things have to get done. I think really the big things for operational management in winter is going to be reduce leakage. A tight barn is going to ventilate the best during the cold weather because we need to be able to develop a static pressure, get good air distribution and mixing for that environment to be optimal. Watch the pigs or birds or cows, whatever they are. They're going to kind of indicate to you what kind of environment they're in and if they're favoring certain spots of the barn or avoiding certain spots of the barn. Check your sensors, make sure they're working and they're clean. And then if we do have to make small changes to the controller, make make sure we do them small and then we watch them. Controllers aren't going to respond instantaneously to a change, so we want to do gradual changes, observe and monitor, maybe make another small change, observe and monitor. The worst thing to do is make a big change and then walk away because it might take 6, 8 hours for that change to have an impact on the environment, and we don't really want that to happen because it could be a bad one. Also, remember controllers don't have all the answers, and a lot of the things um, getting ready for winter have to deal with just being prepared from an equipment standpoint to make sure everything's functioning and doing what it's supposed to do. So key take-home messages, we have to look at the animals and note their behavior. One of the things I do is, ask myself, what is their lying pattern? Again, are they avoiding certain locations? Where's their dunging area? Where are they spending their time? Are they evenly distributed? Are they doing that kind of mix of pattern of lying, drinking, feeding, moving around, right? There should be somewhat uniform. Because if they're all not eating, or if they're all lying, or if they're all doing something, that's generally an indication that the environment's not quite right. Another important part as we um, move into winter is we need to understand what is our outdoor conditions and what is the set point for that barn controller. What stage are we in? What equipment's being called for, or what speeds or openings? And does this match with what it's actually doing, right? If you have the understanding of what is the barn supposed to be doing, and is my equipment and controller matching what that theory is or that concept, right? So if we can start to do that, it's going to give us a chance to identify problems quicker and figure out what's going on. And lastly, just keep routinely inspecting equipment for anything abnormal. We have to make sure everything works, simply turns on and off. Is it going to change open and close correctly? Is it going to change speeds correctly? Is it well maintained? Is it going to fail soon because it has been neglected? We really just want to make sure all that equipment works, because when it gets cold out, if we have heater failures or something else fails or something all switches to on, right, it could result in a pretty drastic change in the environment and be devastating for our pigs. Basics of ventilation, right? It's going to affect everything inside the room. Ventilation is a three-step process. The first step is to bring fresh air in. The second step is to mix and distribute it. And the third step is to exhaust it or take that stale air out. So in wintertime, fresh air in is going to be primarily through our soffits. Whether you keep the north side closed or not, we have to make sure we have adequate soffit um, entry to make sure it's an unrestricted opening and we can get fresh air into that barn. The second step is going to be done with our inlets. So especially for wintertime, we really have to make sure we're getting the correct air speeds. If we have to close some inlets to help drive that airspeed, that's going to really help with that overall mixing and distribution of that fresh air. Because when we mix and distribute, that's how we're going to pick up all the gases, moisture, dust, pathogens, and heat, which eventually leads us to take that stale air out of the barn. And the key component in this is that that barn has to be tight. Any leak is going to allow air to bypass our ceiling inlets and lead to poor distribution. So when we look at ventilation, right, we're going to be spending most of the time in winter, even though it's quite warm outside when we're over on the right side of the graph right now for temperature control. Really, during our cold weather, we're going to be running close to minimum. And during that is the objective is to really maintain the relative humidity at 65, no greater than 70% inside that barn. We don't want to see condensation on water pipes. We don't want to see wet slats. We want to keep that relative humidity under control with our minimum ventilation rate, and that might take some tweaking. So I often like to separate out our CFMs per head and the operation of the actual barn. All right, so a lot of us, if we're at minimum in a wean to finish barn, we're shooting for 1.5, 2 CFMs per pig. Maybe in gestation, you're at 10 to 12 CFM per pig. If you're on the chicken side, you might be at 0.3, 0.1, a half CFM per bird. And all these are great for sizing and selecting the number of fans that you need or the speed of the fans to help get us close to that target. Now, a lot goes into that, and it's not that simple, but at least it's a starting point for saying, hey, I need 224s at 50% running. Then what we need to do is actually compare it to what is the barn actually doing, because there's things like static pressure, wear and tear on motors, distribution. And so then we want to use measurement and observation of the environment and the animals to then adjust those speeds or adjust the number of fans running or where those fans are located to provide that good environment and make sure we're doing what we're supposed to be doing in winter. So we have to have a good design so that there's the capacity and the flexibility to meet those operational and management needs. With a good design, we can eventually adjust it for each barn. They're all unique. And with that good design, we'll really be able to tailor that environment to where we want it to go. So in particular, in wintertime, we have a delicate balance between energy efficiency and air quality. We need both. So as we start to decrease ventilation rate, we can start to save energy because there's less fresh air to heat. That means our heating costs go down. Or if we ventilate more, it's going to reduce our humidity and whatever gases concentrations are inside that barn, but it's going to cost more money to heat. And so what this graph does is shows the relationship between increasing energy demand as we increase ventilation and increasing air pollutants as we decrease ventilation. And so really what we're trying to do is find the sweet spot between how much money we're spending on mostly heating fuel. Also, you could do fan energy, but that's quite minor in wintertime with that air quality inside the barn. So we want to be able to hit our air quality targets, including relative humidity, and also balance with how much money we're spending per pig to heat that incoming air. So for troubleshooting in the barn, here are some key things that I often like to use. Um, Probably the most critical one is a portable weather meter that's going to measure temperature, humidity, and airspeed. You can use this to check your temperature sensors, use this to monitor relative humidity if you don't have a permanently installed sensor. Then also, most importantly, we really need to measure our airspeed at the inlets to make sure we're getting that good mixing. Smoke sticks are very helpful for identifying leaks or seeing those air patterns inside the barn. We might calculate our inlet opening, so we might need a tape measure to kind of get us at a starting point and then adjust from there. And then if you can measure static pressure, it'll be a good indicator of how hard those fans are working if we might have any potential blockages in the system. One could use a laser tachometer to verify the RPMs of the fan blades or the motor, and then compare it back to the manufacturer to see, are we kind of close to where we're supposed to be, and do I might need to make adjustments? It might tell you your motor curve's off, something like that. Infrared temperature sensors are great for shooting floors or mat temperatures. Give you a good idea, is your brooder or your heat lamp kind of putting out as much heat as you were thinking? And are we keeping those surfaces warm so that those pigs are comfortable? Volt or multimeter will help assess how much power is going to the fans and give any indication of some maybe potential electrical issues. Then if you really think there's might be an air quality issue, there's different gas detection tubes or sensors one can wear for hydrogen sulfide, ammonia, et cetera, that kind of give you a more quantified answer to what is the air quality inside my barn at a given time. All right, so let's talk about fans, especially on our swine barns where we have pit fans. They're often the most neglected. A lot of people don't like to walk around their barn with a big snowdrift, so they're very hard to verify if they're working, especially if your controller doesn't tell you the amps that those motors are using. And so usually with pit fans, we really have to make sure that they're clean, well-maintained, functioning, running at the speed we expect, and that the transition is tightly sealed and that we're actually pulling all of the fresh air through the barn and not short-circuiting through the pump out cover or any other gap near that pit fan. Also, since we're slowly getting into manure application season, and Dan will appreciate this, we can't let that manure get too high because it'll eventually act as a restriction and start to choke off that pit fan. So here's a picture of a fan running at 100%, and most would probably say there's no way that fan's at 100% because those shutters aren't wide open. But when that fan is so choked down, the resistance is so high that that fan's barely able to move any air, right? And so what had happened is the manure got too tall or too high in that pit, and we really need at least about a 2 foot minimum to help make sure we have an adequate, unrestricted path of entry from the barn into that pit fan. So what do we want to look for? We want to turn off any unused fans and ideally put some plastic or some blockage behind it, because not only will this help with sealing it up, but it'll also prevent any drafts, leakage, and really help us maintain that static pressure and minimize how much air is going to leak in through the barn versus go through our sealing inlets. If you do seal up and put plastic behind it, those fans have to be off because it's a bad day if that plastic goes through the fan. We want to make sure fan blades, motor housings, wire guards are all cleaned. We don't need any extra resistance, and we don't need the motors potentially overheating. We want to make sure those shutters or louvers are cleaned, functional, intact, because one missing louver in a fan that's not sealed is a really nice, easy way to let cold, fresh air into the barn and not really mix it. Make sure the housing and frames are sealed tightly, and our discharge cones and deflectors are in good intact condition. Switching over to ceiling inlets, since these are what we're going to be primarily using throughout our colder weather months. This is where it gets tricky, right? It's easy for us to change fan speeds or change how many fans are operating, but once we have the inlets installed, and if they're either automatic or manual, getting that good distribution is tricky. So we really need those inlets uniformly distributed throughout the house. And if we don't do this right, we can cause excessive drops in temps if they're manually and we don't set those counterweights correctly. They're too far open, or if we don't have enough airspeed, we're going to create drafts or wet spots right underneath them. And so we really need to make sure that those inlets are managed, checked, calibrated, and are functioning the way they're supposed to. So usually our goal at minimum ventilation is going to be between about 600 to 800 feet per minute. And you'd measure that by putting your kestrel up to the opening, and you really need to be at that spot where the pinch point is, where that inlet allows the air to enter the room, and that's going to give you an indication of how fast is that air moving, and are we getting a good jet for mixing. After you get above min vent, you can be somewhere between about 800 to 1,000 feet per minute, which again is going to help keep a good air jet, keep that cold air up near the ceiling before it gets down to the pigs. So with inlets, if we don't have enough static pressure across that inlet, that cold air is going to have a low airspeed. It's going to drop, create a bad environment. And then as you increase that static pressure, so whether it's from the outside to the room or from the attic to the room, you're going to drive that air in faster. But we also don't want to drive it so fast that we have a really high static pressure across our inlet, which is going to then make our pit fans or sidewall fans work a lot harder. So really what we're looking for is a nice jet with good static pressure. So that's right around 800 to 1,000 feet. That cold air is going to come in. It's going to warm up. It's going to expand its moisture holding capacity. So we can start to mix, pick up that moisture, decrease our relative humidity. And then by the time it gets down to the pig space, it's just going to slowly diffuse, and we should be virtually draft free in that bottom couple feet above the slats. When we don't have the right static pressure or our airspeed is too low, that cold air is going to come down, it's going to fall, it's going to create that wet, drafty spot right underneath the inlets. And then also, more importantly, it creates a dead spot opposite of that because we're not actually able to get that fresh air to the other half of that barn. And so that's why static pressure and inlet airspeed is so important, because when it's not, it creates two bad environments, a stale environment and a really cold environment. And that's no good for anything. Depending on where your temp sensors are, it could lead to the controller not doing exactly what you want. But at the end of the day, in order to get that good airspeed and a good jet, we have to have a nice tight barn. All right, so what does it look like? If you have a row of ceiling inlets down the middle of your barn, that cold air comes in, it drops, and that might be only about 4 to 6 feet during minimum ventilation, and that would be about 200 to 400 feet per minute. And so that's what we're trying to avoid. And we want to get up to that 600 to 800 where we get a good jet and really promote good mixing. See, if that inlet's open too much, right, at a constant airflow, that airspeed is going to decrease. And if we start to close it at the same airflow, that airspeed is going to increase. So it kind of depends on how much it affects static pressure and subsequently the fan, but generally that's how it works. Another thing with inlets is we want to make sure we take the time now to repair and make sure they're sealed correctly. Again, we're going to be using them for the next couple months. So make sure they're intact. We have all the doors on them. They're sealed. Screws are in the right spot. Go through and calibrate them, especially now before it starts to freeze, so we don't risk some of those doors get shut. But now's the time to get the work done on the ceiling inlets while it's still nice outside. Now, I've said this before, but really minimum ventilation success requires a tightly sealed room. All of that air we want to drive through the attic, through the ceiling inlets, and the only way to do that is to prevent leakage and infiltration, skipping that and just taking the short circuit, easiest path of least resistance out through the fan. So what we're trying to do is really control how that air enters the barn and really promote that good mixing. And so some examples of leakage, shutters leak really bad. That's why we recommend putting some plastic behind them, just because they can, sometimes with, a row of tunnel fans, you could easily meet your minimum ventilation needs just purely through the leakage of the shutters. So let's now talk a little bit about controller settings because this is going to have a direct impact on heater runtime and heating cost. And so if we're managing space heaters or forced air furnaces, the important ones here is we need to look at the heater offset and the differential between when the heater turns on and when the heater turns off. So every controller is going to kind of have a different way of saying this, but what happens is when we're below that set point, we're going to be in the heating phase. We don't ever want to heat when we're above the set point because once we're above the set point, we're going to start to enter the cooling phase where we're going to increase ventilation as the room temperature increases. So the differential is between that heater on and off temperature. In this case, it's 1 degree Fahrenheit. The heater offset is the temperature difference between the off temperature of the heater and the set point. In many barns, we often have more heat than we need, which causes the heaters to not run that often. And so when those heaters turn off, the room's going to continue to warm slightly, especially other factors like room size, obviously size of heaters, is all going to impact on how much that room warms up after that heater turns off. But at the end of the day, it takes time for that heat to fully distribute and for the time for that sensor to recognize the warming environment to relay that information back to the controller. So usually we're between at least 1 to 2 degrees below set point is pretty common. Again, it's going to depend on room size and how much heat's available, location of things, mixing, etc. But that's a pretty typical one. So what happens if we turn that heater off too close to the set point? So if that offset is too small, in this case, let's say a 0.5 degree Fahrenheit, that temperature is going to overshoot the set point and it's going to cause the ventilation fans to start cooling. So what you might see is an extra fan turn on, or you might hear that those minimum ventilation fans start to ramp up. You can just notice that by either watching the controller, being in the barn, and just listening. And so we start to see that heating occurring past the set point. Those fans are going to go, and we really should never see that room temperature go above set point. And so we typically call that overshooting, overrun, a lot of different ways to say it. But ideally, our set point in winter is always about 0.3 to 0.5 below set point. And so if you have to make adjustments, make it to the set point, not to the heater offset, because that's going to directly affect heating costs. So if you happen to have variable speed fans that are controlled with a triac, this applies to you. If you have variable speed fans that are controlled with a 0 to 10 volt signal, this is not for you. However, there's still many controllers and fans out there that still control variable speed this way. So a lot of the common questions are, what speed do I use? What's the number on my controller mean? I just replaced my fan motor. Why is my system and environment different now? What happens when I use the wrong settings? So one of the good questions is always, what does 50% speed mean on a controller? If that's what it means and it just isn't a number. Is that half of the CFM, half the RPMs, half of the voltage, or is it really just some funny number? At the end of the day, it all depends on the controller. Some use RPM, some it's kind of a funny number. I've seen it many different ways, but the important thing is understand your controller and what that number means and what your goals are to hit that minimum ventilation rate. So typically on triac controlled variable speed fans, 50% of the speed does not equal 50% of the CFM. 50% of the voltage definitely does not equal 50% of the CFM or RPMs, which we'll get into in a little bit. Every motor is going to react differently to voltage, so that's why we need to fully understand what our motor curves are, what motors we have. Minimum speed should never be under 50% of the RPMs. I've seen, some go 40%. I think more are trending closer to 60% now, just because wind effects and just general fan wear has been causing our minimum ventilation to be quite under of what we're expecting, even though we think we're at 50% of those RPMs. And the way these work with a triac, that controller is going to control that variable speed fan by changing the voltage to the motor, where there's no energy savings, unlike if you look at VFDs or some of the electrically commutated motors. Those are going to have energy savings as you reduce the speed of those fans. So how this works is that you will punch a number into the controller. It's going to be translated through the use of a motor curve, which is going to output a volt. The motor is going to get those volts, change its RPM. Then the fan, as it changes its RPM, is going to affect its CFM. So we don't want to make the mistake of thinking that the percentage readout on the controller is a percentage of full airflow that that fan will deliver. Because that controller is going to change the voltage with the percent readout on the controller, we're going to get a different result. So most likely we're changing the speed, which then is going to affect the CFM or that airflow that fan's going to deliver. So it's important understand your controller and what the proper motor curve is supposed to be. So another thing to always keep in mind, especially on these types of fans, this graph shows our static pressure or our resistance versus the airflow delivered by that fan at the different voltages supplied to that fan. So 230, the red line there, would be the full speed characteristics with the flow rate associated with it. And see, that fan has no problem operating up to a quarter inch of water with only about a 12 to 1300 CFM reduction in airflow. As we start to decrease the voltage to that motor, the RPMs are going to decrease, and the ability of that fan to move air is going to decrease dramatically. So if we notice, again, let's take 230 as our full power. We're at about 7,000 or so CFM at a tenth of an inch of water. At half power, at 120 volts, at a tenth of an inch of water, that fan's only going to move 800 CFM or 10% of its full power rating. So we have to keep this in mind. This is why managing static pressure and motor curves are so important, because we don't want to drop the voltage to these motors so low that these fans are barely moving any air when we really need them to move the appropriate amount in wintertime. So the motor curve is going to describe the relationship between the voltage supplied to the motor and the resultant RPM or that fan speed to deliver that airflow. It's going to be totally different with different motor manufacturers, makes, models, sizes, and there's a different curve for every motor. So the goal here is to get the right curve for your controller to make sure that we change that ventilation rate smoothly as the temperature inside the barn changes. And so that graph shows kind of how a fan responds with in actuality, and really what that motor curve is doing is taking that funny relationship of how the motor responds to voltage and turning it into a straight line, and that's what's going to get us a nice smooth transition in our barn as it starts to warm up inside. So what that looks like is just kind of showing on how nonlinear and kind of funny this is that, you know, in only about
Mo-
638 CFM. You change another 33 volts, you get double the speed change and almost triple the change in airflow. And then 27 you can see. And so that's why this motor curve is so important, because we can't just, you know, change the voltage linearly, because the motor's not going to respond linearly to that change. And so that's why it's really important to get the right motor curve so that we can get that linear relationship for that fan. So again, here's a example of voltage supplied to the motor. Then you have in the blue line the RPMs, and then the red line is the CFMs without the cone. And so again, you can see just this is not a smooth transition, so we don't want to just incrementally change voltage. We have to change it logically so that we get a nice smooth transition. And this is essentially the data from the previous slide. So now if we look at some AP motor curves, just kind of just again show how different these motor curves really are. Let's just pick 90%, for example. Motor curve 1 is 141 volts. Motor curve 4 is 186. Motor curve 8, 128. So you can see that each of these motor curves, when you select 90 on that controller, is going to give a very different voltage to that motor for each of these motor curves. So that's why this is so important, because a fan operating on motor curve 4 versus motor curve 8 is going to be a totally different speed with a totally different airflow rate, which is going to have a drastic impact on heating costs and how that room environment changes as that fan starts to ramp up. This is a busy graph that shows all 10 motor curves for a controller. You know, they're all very different. And again, this is why it's so important to get it right, because if you select the wrong one, that fan's going to respond very, very differently than what you would expect it to, given the correct motor curve. Next, I'll kind of move into curtains and soffits and sensors. Really got to make sure our curtains are tight. And really, it's not so much as a heating problem or like a heating cost problem. It's really a static pressure problem, right? So all those holes are just a bypass spot for air to come in. It's going to create drafts. They're uncontrolled inlets. And so it doesn't take that large of a hole to start to satisfy all of the inlet requirements at minimum ventilation or even slightly above it. So we want to patch holes. They're easy to see. They're a lot easier to do when it's nice outside. It's not fun trying to patch a hole when it's 20 some odd degrees outside with a 30 mile per hour wind. So we want to make sure we get those sealed up and as tight as possible. I'm sure these curtains look like they're in good shape to some people, but again, I've seen some that look like Swiss cheese. So again, just make sure they're patched, sealed, end pockets are in good shape, um, and that we have enough, at least a 2 to 3 inch overlap when that curtain closes to make sure that we're able to actually suck that curtain in pretty tightly so we don't have any leakage coming through any sags or gaps up at the top where the curtain meets the sidewall. Bubble wrap is a good way to kind of reduce that the cold surface radiation heat transfer from that to the pig. If we do put bubble wrap up, make sure we don't go all the way to the top because if you're using that curtain as an emergency drop, we don't want that to be completely sealed with bubble wrap. And so that bubble wrap kind of helps a little bit with minimizing leakage. At least can prevent some drafts from entering right down where the pigs are at, but it also, just reduces that cold radiant surface from negatively impacting those pigs, especially if they're small. Again, since we're going to be pulling most of the air through the inlets, we really need to make sure our soffits are clean. Even bird netting can get clogged, especially after harvest. So we want to make sure we get those broomed off or leaf blown off, whatever it takes to keep those clean because we're going to be pulling a lot of air through there. And don't forget the insulation stops. I know they're somewhat hard to get to, but that's another pinch point that can occur if those stops get jammed up against the roof line. It's just going to kind of block that air from going into the soffit. Sensor location and management, we always need at least 2 probes in case one goes bad. Keep them close to the pig, but not out of reach, but out of reach, so they don't eat it. We don't want them to be directly impacted by heaters or inlets. They kind of need to be in an average area, close to the pigs as possible to give us good information. And so this graph or this image here shows what happened after one cleaned some probes. So you can see that those temperatures changed quite a bit by just wiping off that, accumulated dust and grime that can attach itself to temp sensors. So keeping them clean is important because it'll affect the information that goes back to that controller. So other things, just as I wrap up here, just to keep in mind, we need to make sure we get all of our summer things, especially that are using water, um, turned off, buttoned up, winterized to make sure we don't have any burst pipes or any other freezing issues associated with. So mainly with misters, turn off the lines, clean the filters, power off the solenoid so they don't actually turn on in the middle of winter. If we have evaporative pads, again, turn the water lines off, flush clean, antifreeze if needed. Um, if we need to install some insulation, it's always a good idea to help block, just kind of depends on the barn layout. Then also, make sure we go through and check our backup thermostat. A lot of times I get asked, what's the best backup setting? Well, it all depends on how fast somebody can get there. Sometimes you can have a little bit wider margin if somebody lives really close by. But if it takes somebody 45 minutes to an hour to get to that barn, you might need to err on the side of caution, just because it could take some time before somebody can actually respond to a potential catastrophe. So with that, I'd be happy to take any questions.
Thank you so much, Brett. As a reminder, if you do have any questions, please type them in the chat and we'll get Brett to answer them. I think there's a lot of information there. One of the things that I would ask is what's the most common ventilation problem you see as you prep for winter? What's the thing that often gets forgotten on the checklist?
That gets forgotten on the checklist. So I'd say, I'll pivot that real quick. I think probably the toughest and most common thing is a leaky barn. Now, it's sort of on the checklist, but there's a lot of leaks you just can't do anything about, right? Without spending a lot of money, time, and effort. So really, the leaky barn is probably the most common, but also on the flip side, the most difficult thing to solve, right? Beyond the cracks under the door, the holes in the curtain, stuff like that. Um, that's probably it. But in terms of forgetting something on the checklist, um, I would say, uh, probably just making sure all the equipment works, something like that.
Perfect. And then we have a couple questions for you. One was just they're offering you a job on a sow farm, helping with their ventilation system. But as you think about what you have shown today, what are some of the sow farm tips that you give?
Um, So if we're in farrowing, I think that's where it's most critical to make sure we get our minimum ventilation dialed in and our inlet set right. Just because the risk of damaging little pigs leading to scours or some other health challenges is so high because they're, little piglets. Um, that's why I think it's just critical is making sure we get the right inlet airspeed in farrowing so we're not potentially drafting those piglets.
Perfect. And then can you troubleshoot a problem? What can be the problem, reason, and consequence if we get too high of wind speed or air speed at the inlet?
So that can lead to um, So a few things. So it depends on how close, if you have two rows of inlets, if they're, less than, 25 feet away from each other, what can happen is if that air crashes, it's going to crash and then it's going to go straight down and it's going to be really drafty right where those two air jets are going to hit each other. It can also do the same thing on a wall. So if we're too close to the wall or it's coming out too fast and hitting that wall with enough velocity, it's going to crash straight down. And again, just create more drafts.
And then can you speak to the relevance of rodent pest control and how ventilation leakage can be impacted? And what are your recommendations for pest control?
I think it just comes down to having a good rodent or pest management system with bait boxes and gravel curtain around the foundation or the stem walls. And I'm not truly an expert in the best rodent control strategies, but I'd say following just the general good practices associated with rodent controls just kind of helps minimize that because once you start to get mice tearing through curtains or chewing up spray foam and doing whatever other sorts of damage they can do to that overall building envelope, it's just going to lead to a leaky barn.
Perfect. And then since you mentioned pump outs, especially during manure application season, what should we do when we see those trouble pump outs that fall apart when we take them off for manure pumping? What do we need to do when we put them back on?
Well, probably replace them, but just making sure that they're seated firmly up against the stem wall. Um, I've seen some throw some sort of like a silicone or like a rubbery um, adhesive type thing if you can get it to break off later. Some put in like a bolt that you can kind of tighten down just to hold it in place. Um, Ideally you don't use wood because it warps really badly in a pretty short amount of time. Plastic's a little bit better for that. Making sure your concrete's in good condition, doesn't have a bunch of chunks missing out of it that just lets air through. Just making sure everything's kind of well kept.
Perfect. I think that took us to the end of the questions. Thanks again, Brett, for that excellent presentation. That's a lot to think about for getting our barns ready, but important to do. Once again, thanks everyone for joining us on our adventure through Barn of Tomorrow. We'll be sending out an evaluation for you to fill out to help us determine what we should do next year if we should continue this. But we really appreciate you taking the time to tune in, help us grow this program, and think about what possibilities it has in the future. Any last words, Brett?
Enjoy the warm weather.
There we go. Take advantage of it while it lasts. Thanks, everyone, and have a great day.